Okay, so now let us look at the actual implementation of the AXI peripheral, right. As I said, this is just a simple register bank. So let us take a look at what the code itself looks like. Then we will look at the test bench and try and understand how we could actually simulate, send some data into it, compare the results and so on. Okay. So this code is a little complicated. I have already showed you a couple of different parts of it. So I am going to sort of focus on those, right. The code itself is long. It is well worth sort of reading through to find out what it involves. It is also worth reading it simply to understand that writing Verilog code is for something like the AXI protocol is a fairly complicated endeavor, right, and getting it completely right is not entirely trivial, but at the same time, as long as you follow those handshaking and the waveforms as your primary guide, right, you should be able to get the correct behavior. So the first thing that I want to point out over here in this module is, you can see that there are, let's look at the different signals that are present, right. We have the two inputs, the clock and reset, and as you can see there are a lot of conventions that we follow, right. This A clock and A reset N, these are things which are commonly used in order to indicate the AXI clock and AXI reset, right. Using all capital letters is a common convention that Xilinx follows. By default, there is also the convention that the names of the wires also tend to be in capitals, but there was some problem with Cocotb where it does not recognize some parts of the signal automatically if you use capital letters, which is why I have renamed everything using lowercase letters out here. But let us look at the overall the set of signals that we have. Right. What I have in this case is, there is this so the write address channel, right, the first of the 5 channels that we have in the AXI protocol consists of these 3 sets of wires. The first is AXI AW address, then AW valid and AW ready, both of which are single bit wires. Now you will notice that the address width over here is only 4 bits, okay. Normally I would expect my address also to be 32 bits. Why am I declaring it as 4 bits? Remember what I told you, that the interconnect will in this case decode 28 of the bits and only the last 4 bits will be sent to the actual peripheral, in this case my register bank, right. Because of that I can basically map my register bank into anything which has at least like those 16 addresses corresponding to the last 4 bits of the address space, right. Now after that comes the write data channel, and over here as we saw, right, there is a write data, write valid, write ready. In the original picture there was also a write last, which I have not introduced over here, I have just ignored that. But there is a write strobe, and the strobe signal, as I said, is used in order to selectively write one or more of the bytes that are present in the data. And in fact you can see that the strobe width is determined parametrically from data width. So if I at some point change the data width to 64, the strobe width would change to 8, okay. The write response channel, you can see that the B resp has been declared as a 2-bit value, okay. As I said, the B response is only going to be either OK or error, right. So I just basically need to assign a couple of codes for that, which is why I am just using a 2-bit value out there. What is important though is the valid ready handshaking signals. What about the read address? Very straightforward, AR address, AR valid, AR ready. Read data is R data, and once again I have a R response which is also similar to the B response, 2-bit value. R valid, R ready for handshaking, okay. And couple of things you might notice, there are for example things like the sum of these, right, what are the inputs and outputs, right. In the case of the write address channel, since what I am defining here is the subordinate, the register bank is going to be the subordinate module which is going to get data written by the manager, which is usually the CPU, which means that the write is going to come from the CPU. So the write address and the write valid or write address and the write address valid are going to come from the manager. Therefore, they are inputs to my register bank. The ready signal is something that I need to send back. In this case, it's declared as a wire, as you will see, because of some of them are declared as wires and some of them are declared as registers. You will see the way that the code actually is written, why some of them are written as wires and some are written as registers. Similarly, the data is also coming in from the manager, and therefore the W data, W strobe and W valid are all inputs. The W ready is an output. The write response, on the other hand, is going back from the subordinate to the master, right? And therefore, the B response and B valid are both declared as outputs. And because I will be assigning their values inside an always block, I declare them as registers as well. Okay. The B ready, on the other hand, is coming in because that is from the manager to indicate that it's waiting for my response. Similarly, on the read side, the address is an input, the data is output. Okay. So, these are all the different channels that are required for the AXI interface. Now, you can see that I also defined two parameters. OK is defined as just 0 0 and SLV error essentially stands for slave error, right? That is given the code 1 0. This once again is standard AXI terminology, right? In the AXI protocol, returning a response, a 2-bit response of 0 0 is considered OK, and returning 1 0 instead is considered as there was an error somewhere. Either the slave was not ready to respond, or it couldn't understand what you asked for, or you were expecting something and the slave couldn't perform that computation. Any one of those combinations could happen. Okay. What we do is we use parameters so that it's cleaner, right? We are not directly hard coding data into the remaining parts of the code. And finally, our entire register bank needs to do something. I am defining two registers that will actually store the data that I am trying to write into it. Okay. And you can see that one of them is called reg control, the other is called reg data. I could just as well have called them reg 1 and reg 2, it does not really matter, right. What matters is reg control is supposed to be defined at address offset number 0. In other words, if I write into address 0 corresponding to the AW address over here, it will write into reg control. If I write into address 4, because after all that is the next 32-bit address, it will go to reg data. Okay. So, let us see how that gets implemented. Now, these extra signals over here, right, this handshake done signals are primarily required for the scenario where I can have independent arrival of the address and data, right. So, it is possible that, for example, the AW handshake, that is to say I have received the address for writing, happens before the WHS, that is the W handshake. I have not yet got the data. So, I need to have two different signals that keep track of what state of the transaction I am in, and only after both of them have completed, that is I have got the address, I have got the data, only then I go into the response mode where I send back and I clear both of these. Okay. And that basically is what we are going to do. Similarly, there is a read address handshake as well. Now, the interesting thing is, right, it actually allows us to write our code in a very compact manner. What I can say is this AW ready is a signal that needs to go back from my reg bank to the manager. All that I do is, am I done with the current AW handshake, right? If not, then I say I am ready, because basically this AW handshake done will be false or low whenever I am not in the middle of a handshaking process. But as soon as I have actually got data and before I have sent back the response, this AWHS done will be 1, right. So, like I told you, this AW ready signal is what is finally going back to the manager. The manager does not see the internal AWHS done. All that it sees is AW ready is low until the entire transaction including the B response has come back. The other thing I have got of course over here is any time that reset is low, automatically the ready becomes low, right. So that's just one piece of extra logic that I've got over here. So that's there for all of the signals that I have. Similarly, what about the W ready? Same understanding. If reset is low, then W ready is low, but otherwise if the W handshake is currently done and I am waiting, right, then the W ready is going to be low. But if the W handshake is false, right, then W is ready, I can write new values into the data, okay. And similarly exactly the same thing happens for AR ready. In this case it needs to check for one more thing. It also says check whether the handshaking is done and also that there is valid data coming, right. So in other words, this is sort of or rather the address ready, if there is valid data that has come, I am sending back valid data. At that point I can also send back my AR ready to 0, or sorry, the moment that when I am sending back valid data, I will not accept any new addresses, right. So the AR ready will be low until that handshake on the return direction has completed, okay. The rest of the code, as I said, we already looked at this part of the code which corresponds to the write address, right. So I am not going to go over it again. The important part is that this handshake happens over here. Yeah, so the write address handshaking happens over here, right. I am looking for the SAXI AW valid and SAXI AW ready, and I am using this AWHS done in order to ensure that once both of these signals become high, I am not going to let another transaction happen until the response, write response has been sent back, okay. So if I write one data, now I want to make sure that my AW ready goes low and stays low until I have sent back the response and I am ready to accept the next AW address, okay. Similarly, the write data handshake also happens over here. It once again looks for the W valid and W ready, and I can clear after the write response has been received or accepted. I also generate one more internal signal called do_write, which is actually going to tell my registers when I should capture data and store them, right. And this basically says this should happen when the AW handshake is done, the W handshake is done, and I have not yet sent back the valid for the response, okay, before I send back the valid for the response. And if I do all of that, right, I also have this thing which basically allows me to say I want to, I am looking only at the address 3:2, it is a 4-bit address 3 up to 0, but I want to take 32-bit words, which means 4 bytes. So I am sort of dropping the bottom 2 bits completely, okay. Now with all of that in place, let me look at how the writing actually happens into the register. That is fairly straightforward, right. At this point in time, this does not have any direct interaction with the outside world, but what I am saying is this do write signal high? When would that become high? After both the handshake for the address and data have come in. At that point I check the word select. If it was equal to 0, 0, it corresponds to the control register. So what do? I update the value which is present in the control register, right. But look at the way that I am doing this. I actually have a for loop where I check the W strobe signal and say only if the W strobe signal corresponding to that byte is equal to 1, I will actually write into the register control. Otherwise, I will just leave it as it was. I will leave that particular byte alone and not change it, right. This is actually quite an interesting use of the W strobe signal. I can have a 32-bit register, but modify just 8 bits of it when I need to, okay. And once I have done that, I basically say the B response is okay because I was able to successfully write something, okay. What if the address was 0, 1? It means that I need to update reg data, okay. And I then go in there, do the same thing, I check the strobe and update the value of reg data, and I set the response to OK. I also have a default case statement which says it was an invalid address and therefore make slave error equal to whatever this the B response equal to slave error, which is that 10 some pattern, whatever it was. So in other words, what are the valid addresses that I could have over here, right? I could have either 00 or 01, but if my address came in as 10 or 11, I would get back a slave error from my AXI bus, okay. And finally, after all the do write has completed, I will make the B valid equal to 1, right. And the next thing I check is if the valid is currently 1 and the B ready also becomes high. When does B ready become high? That became high in some other part of the code, right, where I the B ready signal comes from the manager. So the B ready signal comes from the manager. If this handshaking has completed, immediately make B valid equal to 0. Okay. So on the next clock cycle, it will make the B valid signal once again equal to 0. In other words, if you look at this code and you look at the waveforms that we discussed earlier, you should be able to relate each step of this with some part of the waveform of the transactions that are happening out there. Okay. There is also of course the question of what happens in case of reading, right, and it is very similar. It once again looks for the address read ready valid signals. It takes the actual address, and if the address was 0, it returns the value of reg control by putting it into R data and sets the response to OK. If the address was 0, 1, it takes the value of reg data and puts it into R data and returns the value OK. If I try reading from another address, it sets the R data to 0 and then makes the R response SLV error, okay, and once again makes the R valid equal to 1, and if the handshake has completed over here, it makes R valid equal to 0, okay. Once again exactly going through the steps of the handshake and implementing each of those functionalities as it was, right. So now let us look at this. How do I go about testing something of this sort? Can you think of ways by which we would test this? The way that I would normally look at it is, okay, now I have some kind of an AXI interface for this register bank. I need to generate all of these corresponding signals. I need to generate the AW address, the write address, the data, the valid signals, the check for the ready signals, make sure the handshaking is proper and so on, right. That is basically where the power of Cocotb comes in. What I am going to do over there is look at what the Cocotb based test looks like. A lot of this stuff, right, the initial imports and so on are very similar to what we already had. The reset is the same. There is one more function out here which basically says something called make AXI Lite master, right, and here you will see that it basically looks at, there is one function out here which says just create an AXI Lite bus. Now what is an AXI Lite bus? That is something which I imported from the Python libraries. The interesting thing is it basically says do this from the prefix SAXI, right. What does that mean? If I look at the original source code of my register bank, right, you will see that all my bus related signals started with this SAXI underscore. So what that from prefix is telling Python is look for signals that have the name SAXI underscore, right, and all of them basically correspond to a bus. Look for the appropriate write address, read address, AW address, valid, ready, all of those, and combine them together into an object inside Python which corresponds to an AXI bus, okay. So it sort of does a lot of interesting magic out there behind the scenes. and what we find is that our actual tests start to look extremely simple, right. All that I do is I make this AXI Lite master and I call this function AXI Lite.write. Okay. I give it the address 0, and this part looks a little complicated, but basically what it's saying is take the number 1, the integer value 1, convert it to a 4-byte value, right. That is what this 1.2 bytes. Okay. This is basically a Python function which takes a number and converts it into an array of bytes, right. And it also says to use the little endian byte ordering. Okay. Now that is the default, so this was not strictly speaking required, but it is interesting to know that you can actually sort of switch byte orderings and work with different buses if you need to in this Cocotb. Okay, so all the stuff that we needed, right, set the value of AW address, do the handshaking of read the valid ready and so on, set the value of the write data, wait for the B response, all of that is one line of code over here. Okay. And similarly after that I have another line of code which writes into the other register, which is address number 4, and gives the value 1234, converts that to bytes and sends that out here. How do I test whether this worked? I read back from 4. How many bytes? I read 4 bytes. I convert those bytes into an integer and verify that they actually match the value 1234, which was what I wrote originally to start with. Okay. So this looks like a reasonable test. Along with that I have also got one more test which is what is called a partial write test. In this case once again I go write the reset condition, then I make the AXI Lite master. I start off by writing this value 1 2 3 4 5 6 7 8 into register location number 4, and then after that I write only 2 bytes, right. What you can see over here is I am basically giving this value B and just giving 2 bytes alone. Automatically the Cocotb test bench understands that it should make the strobe signal such that only 2 of the bytes are written and the other 2 are left unchanged. How do I test that? If I read back 4 bytes from here, I should now find that only this 5 6 7 8 got replaced by ABCD. The order will be reversed because of the little endian, right, and I should check that my final value comes back as 1 2 3 4 ABCD. Okay. So all of this essentially can be sort of, as you can see, the test actually in Python became extremely compact and easy to read and understand, right. If I wanted to create more complicated test benches where I write multiple values into different locations, change the order in which I write and read and so on, all of that would just be like a few lines of code. What would it look like when I actually run this simulation? Let us go ahead and try that, right. I can run make as usual. It will go ahead, what it does is it actually compiles the entire Verilog code into a C program. That is how the Verilator simulator actually works, right. As you can see over here, it is actually going ahead and it is calling the C compiler in order to do the things. You do not need to do any of this, Verilator automatically handles it for you. It also creates whatever interfaces are required between the Python and the Verilator so that the entire communication can happen, right. And as you can see, it basically ran 2 tests. It says that both the tests passed. You can see how long it took for each of the tests to run, and there is also some useful information about what buses it identified and so on. And finally, sort of to top it off, you can also open the waveform, right, that it dumps out over there. We can look at the entire interface corresponding to this AXI reg bank, and if I find that there are quite a lot of signals out here, but if I zoom out, I can pretty much see all of the AXI handshaking that is happening out here, right. I can basically group the signals together. I can start off with the address AW valid, right, where would, yeah, so I have AW valid, AW ready and Yeah, so these three values, AW address, AW ready and AW valid, essentially constitute some handshake that happens out here, right. Similarly, there is the write data, the write valid, write ready, which constitutes another handshake. There is the B response which happens after that. Each and every one of those can be systematically followed up in this waveform, and you can see how those different combinations work. Okay, so to summarize, the point of this exercise was first of all to recap how memory mapped IO works, how we can implement something like that in a simple Verilog code corresponding to a register bank, and how using Cocotb over here helps us to very easily simulate the fairly complex AXI protocol and test different kinds of functionality with it.